All right, let's pull back the curtain on the invisible world of electronics. Today, we're talking about two tiny components that have had a massive impact. These are the hidden architects behind the rhythm of our digital lives, and we're going to see exactly how they pull it off.
I mean, really stop and think about it. How does a simple kitchen timer know exactly when to go off? Or how does your car radio grab one specific station out of thin air and just lock onto it? Well, the answer isn't magic. It's just some truly beautiful engineering, shrunk down to something smaller than your fingernail.
You see, at the heart of it all, it's about the precise control of two things: time and frequency. Our entire digital world, from the simplest flashing light to the most complex signal from your phone, is built on a foundation of perfectly timed pulses and rock-solid frequencies. And it's all managed by these microscopic little guys.
And that's where our two heroes for today come into the picture. We're going to explore the stories of two parallel legends in the world of integrated circuits. First, the incredibly versatile 555 timer, a true master of time. And second, the ingenious phase-locked loop, or PLL for short, the undisputed master of frequency.
Okay, first up, let's meet the king of timing circuits, the 555. Seriously, for over 50 years, this little chip has been the absolute go-to for anyone, from hobbyists to engineers, who needs to create an accurate time delay or a steady, repeating beat. It's a true workhorse.
So what is this thing? Well, the 555 is a remarkably stable and reliable little chip that first showed up way back in 1972. The best way to think of it is like an electronic stopwatch or maybe a metronome on a chip. Its entire job is to generate these precise, totally predictable pulses and time delays.
Now, if you look at the full diagram, it can seem a little intimidating, but the idea behind it is so clever and actually pretty simple. Inside, you've basically got a little team of three parts working together. You've got two voltage gatekeepers, their technical name is comparators. Then there's a simple memory switch called a flip-flop, which all it does is remember if it should be on or off. And finally, you have an output stage that sends the final signal out to the world.
And here is where the magic happens. They all work in this perfect little loop. See, the gatekeepers are watching an external component called a capacitor, which is kind of like a tiny, super fast-charging battery. When that capacitor's voltage hits a certain level, the gatekeepers yell at the memory switch to, well, flip. This flip turns the output on or off. It can also activate another little switch to drain the capacitor, which starts the whole cycle over again. It's this beautiful, constant charging and discharging that creates a perfect rhythmic pulse.
So this really simple mechanism gives the 555 two main superpowers, if you will. It can either act like a one-shot timer, creating a single, precise pulse when you tell it to, or it can be set up to just oscillate on its own, forever, creating an endless, steady wave.
And those two modes are exactly what you're seeing here. Over on the left, that's the monostable or one-shot mode. You poke it with a trigger, and bam! It produces one clean pulse of a very specific length. Think of a toaster timer. On the right, that's the astable mode. It just keeps running on its own, creating that square wave heartbeat you'd need for something like a flashing light.
Okay, so now let's shift gears from the master of time to the master of frequency. If the 555 timer is a trusty metronome, the phase-locked loop, or PLL, is a much more complex and, well, subtle instrument. Its job is to listen to a frequency coming in and then perfectly, absolutely perfectly, match it.
You know, the best analogy for a PLL is a musician playing in an orchestra. They're constantly listening to a reference pitch, right? Maybe from the lead violin, and they're constantly adjusting their own instrument to stay perfectly in tune, matching not just the note, but the timing, the phase. Well, a PLL does exactly that, just with electronic signals.
So how does it manage to stay so perfectly in tune? It uses this really clever feedback loop, which is what this diagram is all about. It takes an input signal, it compares it to its own internal signal, and then it uses the difference between them to adjust its own signal until they match perfectly. It's this continuous process of listen, compare, adjust, listen, compare, adjust.
So let's break that loop down real quick. First, you have a phase comparator. Its only job is to measure the difference between the signal coming in and the PLL's own signal. Then, that difference gets smoothed out by a low-pass filter, turning it into a steady control voltage. And finally, that voltage gets fed to a voltage-controlled oscillator, or VCO, which is just a fancy name for an oscillator that can change its frequency. The VCO uses that voltage to speed up or slow down until the difference is zero, achieving what we call a perfect lock.
Now, there are two really important terms you got to know here. The capture range is the narrow band of frequencies the PLL can first find and lock onto. But once it has that lock, it can actually track the signal over a much wider lock-in range. The best way to think about it is this. The capture range is like trying to spot your friend in a massive, noisy crowd. But the lock-in range is how far you can follow them once you've found them. See? It's always easier to track something than to find it from scratch.
So, we've got the master of time and the master of frequency. But why does any of this matter? Well, it matters because these two tiny chips are, and I mean this literally, absolutely everywhere. They're providing the quiet, rhythmic foundation for the world around us.
I mean, look at this. The humble 555 is a true jack of all trades. Yeah, it's used to make simple pulses and waves, but it's also the brain inside things like traffic light controllers, kitchen timers, and even monitors that protect your other electronics from bad voltage. Its versatility is just legendary.
And then you have the PLL. With its sophisticated frequency locking superpower, it handles some of our most demanding communication jobs. That ability to lock onto one frequency is exactly what lets your FM radio pull a single station out of the air. And its ability to generate brand new, stable frequencies is what lets our phones and Wi-Fi routers handle those complex streams of data.
And really, that's the big takeaway. From the simple blink of an LED being driven by a 555 to the incredibly complex, high-speed data being decoded by a PLL in your phone, these two components are the fundamental building blocks. They create the invisible, perfectly timed, and precisely tuned foundation that our entire modern world is built on. It really makes you wonder, doesn't it? The 555 and the PLL are just two of these hidden architects. What other microscopic marvels are out there, quietly orchestrating the incredibly complex symphony of our digital lives? Something to think about.